Yeah. All right. Okay, so today, guys, what I want to do is clear up. I want to clear up a couple things about the difference between the parent population and your sampling distribution. Okay, I want to just really make sure we solidify the quality of. So first off, this is kind of like one little demonstration I didn't do for you yesterday. And so let's talk back about the times to, whatever. I'm going to say times to run a mile or run however. And for me, well, it says the mean here is 16, so let's just say to walk a mile or something. No. Okay, so you know that with this parent population, it is individual times that are in here. Every single time that was taken is a piece of data value in here. These are individual pieces of data. Now, I didn't talk about yesterday what happens if the parent population is normal. Then, whenever I drop down means into the sampling distribution, the collection of all the sample means, what is the shape of that one? So we skipped that little tidbit yesterday. So let's talk about it now. So you were just going to totally guess, what would you think that the shape of the sampling distribution will be if the parent population is normal? You think normal? Okay. So let's see. I actually am going to do sample sizes of 25 because that's this close to the central limit theorem number that, of 30 that this applet will let us do. So here we go. I'm going to animate. We're going to drop down. Here comes 25 individually selected times. We're going to average them and drop it down. There's the average of the 25. There comes another 25 times. We're going to average it. All those 25 get averaged and we drop it down. Okay, so we'll do this one more time and then we'll speed up and do lots of them. So here we go. Average those 25 and there you go. So let's do 1,000 of those things. Boom. See what you got? You have got a unimodal symmetric shape as well. So if the parent population is normal, then here we got this. Now, that was kind of, the sample size was big enough anyway. So let's clear this out. Let's see what happens if my sample size isn't even big enough. It's just 2. Is this still going to produce me a normal model? There's an average of 2. Here comes another average of 2. Here comes another average of 2. And so on. Boom. It is still. So, the moral to this story is, if the parent population is normally shaped, then anything that drops down out of it, even something as small as samples of size 2, is normally shaped. Okay, good? All right. Now, let's go back to one other little thing. Let's pretend like I got something that's skewed. I'll skew this one to, this is skewed which way? Right. This is right. Tail right, skew right. Some people think it's left because there's a lot of data here. No. Here's what skewed left would look like. Let's do skewed left. Because this actually is a question that this first one here on your homework, on the last page of your homework says. It says this. A sample is chosen from a population that is strongly skewed to the left. Okay, so what's happening is the population is skewed to the left. Well, let's look at that. Here we go. I got a population. It's skewed to the left. The question says, what's going to happen if you drop down samples that are small? What shape do you think the sampling distribution will be if I'm dropping down samples that are small? What do you think? You think it'll fix itself and then undo this skew to the left? Okay, so you say yes. Let's see. Here comes, I'm going to animate it. Here comes 2. Drop them down. Here comes another 2. Average it, drop it down, and so on. So let me speed up this process. Here we go. Now look. Would you say this is still slightly skewed left? It is still skewed left. It's better, but it is still skewed. So see, look. If you got a bad-looking parent model, then if you don't have sample sizes that are large enough, you will not overcome this poor shape, and you will still have a skewed distribution. So, like yesterday, let's fix it. Let's make this as large as I can, 25, that's close enough to 30. So here we go, you ready? Here comes 25 pieces of data. I'm gonna pull that down, and once I do that a whole lot of times, boom, there I've got a normal model. Okay, so it being large, in fact, if this was 30, you probably wouldn't even have that little kind of anomaly right there. All right, so in summary, if the parent population is normal, anything drop down can be normal. If the parent population is messed up, then you've got to have large enough to fix it. All right, now, last thing before we start doing some actual writing down of some problems. Let's go back to this thing being normal. Okay, see this thing? All right. It has a mean of 16. It has a standard deviation of 5. I'm going to drop down samples of size 25. Here comes one of them. Average those 25 items. Drop it down. Okay, I'm going to repeat that 1,000 times. There it is. Boom. Okay, so this is beautiful, normal curve. Let's talk about the qualities. The shape of the top one is, the shape of the bottom one is, they are both normal. The mean, the center of the top one is 16. The center of the bottom one is, yeah, right at 16. So the centers are the same. The standard deviation of this top one is 5. The standard deviation of this one is about 1. Why? Because of the square root thing on the bottom. That's right. Very good. Remember yesterday, the standard deviation of the parent population is 5. The standard deviation of the sampling distribution is 5 from up there, divided by the square root of n. So, bum, 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 that makes it 1. So, what are some words to describe this distribution in comparison to the parent population? More condensed. Good, I like that. So, this one down here is more condensed. How about less spread out? How about, yep, less varied. Good. It is more closely clustered around the mean, okay, or the center. Very good. Those are all correct things. All right. Now, last thing I want to talk to you about this is, let's suppose I want to see how fast I can walk my mile, okay, or skip it. We'll do skipping the mile, whatever. Whatever it is that gives me about 16, okay, on average. So let's see, I'm skipping a mile, I average 16, I want to skip it, and I want to see what's the probability that I average 15 minutes or less, okay, because that's like my goal is to average 15 minutes or less on this skipping this mile. So let's look at that. I'm going to actually kind of use a clear page to demonstrate this real quick. So here we go. Here is our parent population, individual times to skip a mile. Okay, we're going to skip that mile. The mean is 16. The standard deviation is 5. All right, here comes this drop down one with samples of size 25. So I got the sampling distribution. The mean is still 16. Standard deviation of this sampling distribution is 1. All right, so my question is, what's the probability that, see, I've tried to make those means about the same. Boom, here is 15 minutes. or less. Let's compare those areas for both of these situations, just to really solidify the difference in the computation of what's happening here. Okay, here's my question. What's the probability that I will put all these times in a bag and I will get one time pulled out of the bag that is less than 15 minutes? Do that. So how am I going to do it? Okay, 15 minus the mean over the standard deviation gives me negative 0.2. I want to go below that, so I'm norm CDFing it from negative 99 up to negative 0.2, and that is about 43, or it's 42.37. I don't know, something along those lines. I think I got those numbers mixed up. Actually, I think it's 42.37. Make a check. Yeah. Okay. Oh, 0.07. Okay. All right. Well, then let's see this. The question asked on this bottom picture would be this. The probability. Can I pick an individual piece of data on this bottom picture? No. What I can pick on this bottom picture is an average of a group, an average of a sample of 15. That's what I have to pick on this bottom. So the question is not what's the chance that I have an individual that is less than 15. The question is what's the probability that I pick a collection of 25 times that average less than 15. And let's see what that becomes. So we're going to z-score that. Different standard deviation. So my z-score is negative 1. So I'm going to norm CDF that thing from negative 99 up to negative 1, and I'm getting 15.86%. So, what do you have to say about that? Is it more likely to find a time that's less than 15 minutes or an average of 25 times that's less than 15 minutes? A time is much easier to get than an entire average of 25 times. Think about it this way. It's harder to move an entire average, right? If you're in the 5th week of the 6 weeks, it's harder to fix your grade. Because you got to move an entire average, not just get one grade better. Okay, does that make sense? And computation-wise, what's the thing that makes the difference between these two pictures? The computation of these two pictures. The one item.
Standard deviation.
The standard deviation. Correct. Here it was 5, and here it is 1. So that's the thing that creates the difference in these pictures. Okay, very good. Now, let's go to this homework. Actually, I think I'm on the just go to the back page. We're on the back page of last night's homework, chapter 18, part 2. We'll kind of walk through this, make sure we kind of understand the details here. So, kind of already talked about this one. The first problem says, what's the sample? Okay, a sample is chosen from a parent population that is skewed to the left. So that means, let me erase all this stuff. What? Who's singing? What are you singing? What are you singing? Okay. We want skewed to the left. They're skewed to the left. Okay, skewed to the left. Parent population, skewed to the left. The question on the assignment says, describe the drop-down sampling distribution with sample sizes that are small. I'm actually going to accentuate that on this by making sample sizes of 2 because it just shows it better. What's this shape of this sampling distribution? Dun, dun, dun. What is it? Still skewed left. Okay? So that's what you have written here. Number 22A. It was still skewed left because the sample size was not large enough to overcome the messed up parent population. Okay, next. What if we made the sample size larger in terms n is greater than 30? What's going to now happen to that sampling distribution? So I don't have that ability to make it 30. I'll make it 25. What's going to happen? Boom. It gets what? Fixed. And now it is normal. So what we have here is this. The shape of the dropped down sampling distribution is now unimodal, symmetric, and approximately normal. It has the same center as the parent population. Look. Look here. Oh, that, yeah, 23.63, 23.65, pretty much the same. So the center is now the same. And spread, we've already talked about this, the standard deviation is smaller than the parent population. Okay, let's look at it. Standard deviation here, 6.39. Standard deviation here, 1.29. Again, what made the difference? Yep, square root of 25 on the bottom, divided it by 5. All right, very good. So C is just kind of an extension of that question. As we make the sample larger and larger, as n gets bigger and bigger, what's expected to happen to the distribution of the data? And you all told me this already. It becomes less varied. It becomes more closely clustered around the mean. It has a smaller standard deviation. Okay, so good. We're already good with all that. Now, 25 takes you through making sure you catch which standard deviation you need to use when you do your computation. Okay? So, let me tell you something. When you read a problem, you should think of two things. When you read a problem, you first need to go, is this a mean or is this a proportion problem? Okay? That's one thing that your brain has to think of first. The second thing that your brain has to think of, am I talking about the population distribution? Am I talking about that parent population? Or am I talking about a sampling distribution? The reason it's important is because the standard deviation will be different depending on which one those are. Okay? So that's the primary two things that you have to assess before you get into computing a problem. Okay, so here we go. On this number 25, when we read that this is assuming the duration of human pregnancies can be described by the normal model, what are they saying? Are they saying this is a parent population, or are they saying this is a sampling distribution of human pregnancies? Yeah, it's a population. They are saying that, there we go. They are saying this. Here's number 25. Here's the problem. This is a pregnancy. This is the length of your mama's pregnancy. This is the length of my mama's pregnancy. This is the length of my pregnancy. And so on and so forth. These are individual pregnancies, and the mean, it says, is 266, and the standard deviation is 16 days. So these are days. All right, so now, here we go. What percentage of pregnancies? So we're not talking about an average of pregnancies. We're just talking about the individual pregnancies. So I am computing from the parent population with a standard deviation of 16. So to find that between 270 and 280, do your z-score using the standard deviations of 16. Okay? And then you calculate that area. And so what we're doing is collecting this picture from here to here, and we're finding this area on that picture there. All right. Okay, next. 25B. At least how many days should the longest 25% of all pregnancies last? Longest 25%. So that means it's this section up here. The question is, how many days is this location right here? We haven't done a problem like this in a while. This means you are solving for x. Let me get a better picture of this. You got this going on, 266, mean of 266, standard deviation of 16. The top 25%, and we're wondering how many days is this? So what do I need to figure out at this location first before I can count how many days that is? So z-score for it. Now, the most common mistake for this problem is that people think the z-score is 0.75, because that's what's below this. The z-score is not 0.75. It is not 3/4 of a standard deviation up. Actually, I probably drew this too. I drew this too far in. Okay? It is not 3/4 of a standard deviation up. Let's see here. Okay, I need to find this location that has 75% below it, and I get that from going inverse norm of 0.75. That is 0.6745. So this place is 2/3 of a standard deviation up, not 3/4 of a standard deviation up. A small difference. If you used 0.75 in this problem, you actually probably got a pretty close answer, but it's supposed to be the 0.6745 standard deviations up. So then, when you go in here and you compute it, it looks like this. 0.6745, solving for x, with 266 is the mean, and 16 is the standard deviation, so that's about 277 days. Alright. So, 25C says this. Suppose a certain obstetrician is currently providing prenatal care to 60 pregnant women. What has that statement right there just now done to this problem? It has now made it a sampling distribution with samples of size 60. That's weird to me. I've always thought that just because you're talking about samples now, we're talking about sampling distribution, but yes. They mentioned talking about samples and asking about the average duration of these patients. That means that they are getting an average of the 60. Therefore, we're talking about that sampling distribution. Okay, so let's read what this one's saying. It's saying, or asking, according to the central limit theorem, what will the distribution of the sample be? What shape will this drop-down distribution be down here? This one's going to be down here with samples of size 60. It'd actually be even a little better looking than that one. Okay. By the way, what will the mean of this one be? Oh, that's standard deviation. Never mind. The mean of it's going to be the same as up here, 266. Its standard deviation is going to be 16 divided by the square root of 60, which is like 2.066 days. This one had a standard deviation of 16 days. This one has a standard deviation of 2.066 days, and it's more consistent, yada, yada, yada. So, there are two reasons that this thing is shaped normally. Tell me two reasons why that I know that that is shaped normally. Number one. No, not standard deviation. N is greater than 30. So the central limit theorem holds. Good. But even if it wasn't, even if it was a sample of 2, why is it still normal? Good. Because the parent population was told to me to be normally distributed. So there were two main reasons that I knew the sampling distribution was normally shaped. All right. Last question. What's the probability that I get an average of 60 with 260 or less? And so that's saying, you know, I got something really skinny. Here's 266. In order to get an average of average be all the way down here at 260, that's going to be very small. Notice the standard deviation I use is 16 divided by the square root of 60. All right, so in summary, today, I need you to fully understand what drives the shape of parent versus, sampling distribution. Okay? And I need you to fully understand when you read a problem, are you going to be computing something off of this parent population, which just uses the regular standard deviation, or are you computing off of the sampling distribution, which uses a smaller standard deviation? Okay? So that's your goal to really hone in on today. Make sure you got that covered. All right. So let's start the assignment for today, and we'll go through some of that. And hopefully you'll have quite a bit of time. If you work diligently, you can maybe get a lot of that done and not have to do that tonight, which you won't be able to. So here we go. Chapter 18, homework part 3. Assume 30% of students at a university wear contact lenses. Okay, so that 30%, what's that? Is that an N, a P, or a P hat? It is a P of the proportion of all students at the university that wear contact lenses. That is the full P. That's the proportion of the whole population. Okay. A, we randomly pick 100 students. Let P hat represent the proportion of students in this sample who wear contacts. So, based on that wording of that sentence, does this scenario imply a parent population distribution or a sampling distribution? Sampling with samples of size what? 100. Very good. All right. Let's check the distribution to make sure it's normally distributed. So people, get real. Check that normal to see if it is normally distributed. Get real. Okay, so that's going to help you remember what you have to do. So what's our first condition? Random. So, read the problem. We, what? Woohoo! We randomly picked it. So therefore, randomness is stated. Yay! Done. Check. Therefore, we are inferring that it's a reasonable representative sample of the students at the university. Okay, see, I like it when it's stated because then, boom, that's a really short sentence. I don't have to say, it's assumed to be reasonable, blah, blah, blah. Okay, I, what's that represent? Independent. Okay, very good. Now, this is that thing, think of your M&M bag. This is when I'm saying your M&M bag is not affecting the portion of whatever in your M&M bag. They're small enough because there's billions of M&Ms. So it's got to be small enough to not change the probability from sample to sample. What's the small enough condition here? Got to be small enough, but then at the same time large enough, so it's going to be just right. Okay, we want our sample of 100 to be less than 10% of all university students. I guess at this particular university. So let's think about that for a second. All right. 100 would be 10% of how much? 1,000. Do you think it is reasonable that a university would have 1,000 or more students?
What?
Yeah, I think so. So I'm going to say I think that's reasonable. It's a reasonable assumption. I mean, yeah, I'm jumping to an assumption. Is that going to apply to all of them? No, but most, yes. All right. What's our last one? Large enough. And so, what do I do there? Oh, you got it. I was expecting somebody to say, oh, 100's greater than 30. Anybody thinking that? Okay. I don't know. Well, you're just so smart because, look, don't forget that the large enough has fractions. Are you mean problem or are you a proportion problem? If you are a mean problem, then your large enough is greater than or equal to 30. But if you are a proportion problem, which is what this is, because it's talking about percentages of students, then it's at least 10 successes and at least 10 failures. So large enough for proportions is NP and NQ are greater than or equal to 10. That's what we're doing here. Okay? So get that straight. Large enough is mean or proportion dependent. Alright, so let's write that out here. So good job, Sarah. You caught it. So NP is 30. That's greater than or equal to 10. So I'm covered. And if 30 of them are successes, then how many of them are failures? 70. And that's also greater than or equal to 10. So I'm done. And therefore the conclusion to getting real is that what? Normal model is appropriate. Or I think shorter, maybe say normal model applies. That might be a little shorter. Yay! So that's our conclusion to those conditions. All right. So our mean of the sampling distribution of proportions is 30%. Very good. And the standard deviation of our sampling distribution of proportions is, got to do that formula. That's 4.58 percentage points. A question. Hey, I get a sample, and you know what? I found that there were 35 contact lens wearers in it. Am I alarmed? Right now, your brain should kind of be having some common sense going on. Am I alarmed? No? Why not? That's about 5%. So 30 plus 4, that's all. 35 is just a little more than one standard deviation up. I'm just kind of approximating. So that's no big deal. That's happening just because of sampling variability. All right. So here, then, with this one, says what's the probability that more than 1/3 of this sample is going to wear contacts? My distribution filled with samples of 100 is centered at 30%. And how do I do more than 1/3? What's down here? What's that line? 33, 3rd% repeating, yada, yada, yada. So you're going to find your z-score and do your norm CDF, and you're going to write this way. The probability that I get a proportion in my sample of 100 that is more than 1/3 of this sample is whatever your answer is. Okay. Now, we're going to do a little bit of this next one just because it's my favorite problem. And it's not that hard if you really kind of understand what the problem's asking, so let me guide you through it. All right. First, do you remember at the beginning of the year, I showed you these little video clips, and one of the video clips I showed you was about the Lay's potato chip factory. And we had a big old truckload of potatoes showing up to the factory. You remember that video? And then we had the guy, and he went and he was stepping on those potatoes. Remember, he was carrying those buckets, and he was stepping on top of those potatoes in the truck. He put those buckets out, and he got 5 30-pound buckets of potatoes. All right. Then he went over to the side, and he did and the little lady tested him, remember, and she was in the factory, and she said they're going to decide to approve that entire truckload of potatoes based on that little old sample of 150 pounds of potatoes. Okay? And so she came out and she said, looks good, guys. Go ahead and we're going to accept your shipment, load up your truck, and if you remember at the end, that's one of my favorite parts. They put the truck on there, and then the whole big truck is, you know, remember, is raised up and all the potatoes are falling down. Okay. Anyway, this is similar, so that's kind of what happens in real life. So look at this. This is a truckload of apples. Instead of potatoes, it's arriving at the packing plant. They do have a random sample of 150. I wish that I should fix this. I'm like, 150 what? Apples? 150 pounds of apples? What? Okay, so I'm not liking that doesn't have a unit, but here we go. Whatever 150 is selected and examined for bruises, discoloration, and other defects, the whole truckload is going to be rejected if more than 5% of the sample is unsatisfactory. So, suppose that in fact, Farmer Joe knows he's got a bum truckload of apples. He knows that he has got 8% of his truckload that are a bunch of bad apples. Oh, maybe. See, that'd be bad. Then they'd get a biased sample. But we're going to say they're randomly on there, but he knows in his mind, man, I got a bad truckload. I sure hope it gets approved, passes inspection. So, this 8%, is that representative of P or P half? That is the P for the truckload. It is the real deal. This is the real factual information about the truckload's percent of bad apples. The 5% is what he is hoping they collect. He's hoping they collect 5% or less bad apples in their samples. That's what he's banking on. All right. So anyway, first question, is this distribution about a parent population or a sampling distribution? Sampling distribution of samples of size what? 150. And unfortunately, the bad writing of this problem, I don't know, 150 apples, 150 pounds, whatever. Okay, so you're going to check your conditions here and so on, but I want to go to the top of the next page and kind of guide you through this real quick, and then I'll let you see why I come around stamp you. So last thing, you're going to figure out the mean and the standard deviation of this distribution, but basically, we've got a situation where these are going to be all of the samples on the truckload. Okay, and these are going to be and it's going to be filled with the proportion that are bad apples. Okay, samples with n equals 150, whatever. So on average, they're going to be 8%, because that's what the truck contains. So on average, it should be 8% bad apples. And we haven't computed the standard deviation, but what samples does Farmer Joe hope that they come up with? He's crossing his fingers and holding his tongue just right, and he's hoping that one of these P hats that guy gets is where? 5% or less. Yep. He's hoping, there's the 5% mark, that guy that goes on top of the apples and gets the bucket loads is getting a sample down here in this region. And so that's what your job is, to figure out what's the probability that the random sample the guy picks when he goes and walks on those apples is one that is at 5% or less. Okay? So that's what this problem is read this. What's the probability that the shipment will be accepted anyway? This means that, what's the probability they get a random sample that shows less than 5% were defective, even though the reality is that 8% of the truck is defective? Okay? So I'm going to let you finish your computing and filling in some of those blanks and work on this for 15 minutes while I come around and stamp your last two assignments. All right. And so this is due tomorrow. You'll finish this up.